Just About Sailing, November 2019. Right, this one is all about the Chinese diesel heater in the real world and condensation. I want to run the boat so that I can heat the boat up to about 22 degrees and about 50% relative humidity, which has been defined by several people as the absolute comfort level. This is the nicest comfort that you can kind of have. And at the same time, I want to avoid condensation because, as we all know, if we've lived on a boat, condensation is a complete nightmare. I've never had a problem with condensation, basically because I've used a desiccant dehumidifier when I've been plugged into shore power, but it uses a lot of power. So there's something that I've talked about occasionally, and that is whether or not I take the air intake for the heated air that comes out into the cabin from the outside of the boat or from the inside. And I've kind of casually mentioned a couple of times that I'm thinking of taking it outside because the air is drier outside, because colder air is a lot drier, and that keeps the relative humidity down. But I've never really justified that, and I've never really tested it. So the next video, I'm actually going to test that in practice. And I think the answer's going to be clear, so prove me wrong, and I might prove myself wrong. I think the answer's going to be clear that there will be a massive advantage in taking the colder air with less water in it from the outside. But that's what I'm testing in the next video. But what I'm going to do in this video is go through the theory of it. Now, if you look at this equation here, yeah, that strikes fear into me as well. If you don't like that sort of maths, because that's how to calculate a dew point, and the dew point is when condensation happens, then don't worry, we're not going to do maths here. We're going to use the power of the felt pen and actually draw out and show you how to work out what the dew point is, the relationship between dew point, temperature, relative humidity and so on, and how that affects condensation and so on. So this video is really for those people who, and I've talked to a few people, so I know that this is something that causes a lot of confusion. A lot of people say, well, what is relative humidity? Surely relative humidity of 100% means pure water. No, it doesn't. It really doesn't mean that at all. So if you already know this stuff, skip this video, but I will talk about relative humidity and dew point and all that sort of things in the next video, assuming you understand it. So watch this video. Do comment below if you think I've gone too simple. I don't think I've gone too complicated. And make any comments and points that you want to, or if you've got a different view of looking at things. So enough of the waffle. This is going to be a talky video, so if you don't like that sort of thing, then do tune out now. I think this stuff is important, and I find it fascinating, to be quite honest. But anyway, once you get to grips with, have a look at this graph. This looks complicated. I'm going to show you how to use that as a real useful tool to actually work out all this stuff, and this could save you a lot of hassle. Right, so this is the important graph, and if you understand, or hopefully if I can explain the basic concepts of this, the whole mystery of condensation, dew point, humidity, relative humidity, etc., and the relationship between all those will go away. So basically what we've got here is absolute humidity up the side in grams per meter cubed. So this is the actual amount of water. Imagine you had a meter cubed square of air and you could squeeze all of the water out of it by some magical principle. So I've strayed from physics already and talking about magic, but you could get all the water out of it. This is the actual amount of water in grams per meter, in grams, that you would get out of a meter cubed. A gram is the same as a milliliter, by the way. So that's absolute humidity, very important. Along the bottom we have got air temperature in degrees C. I prefer working in degrees C. You can get these charts with furlongs per foot squared, or whatever your preferred unit of measure is. That's just a conversion thing. So 0 is here, minus 5, up to sort of room temperature, which we like, which is about 22 degrees. That's comfortable. I'm dealing more at the sort of the lower end because of where I live in the UK and the fact that I think my initial years of cruising are going to be in Scotland, which is kind of colder. And here we've got relative humidity up this side. I'm going to leave that for a little while. This line is absolutely clear, key. I've got here saturated, and that's the air, because air comprises many components. It's got oxygen in it, it's got carbon dioxide, it's got nitrogen, but it also has water vapour. Water vapour is actually part of the air that we breathe. There is a certain amount of water vapour in the air that we breathe, and this is impossible to get to. It's impossible to get above this line. This line is the maximum limit of the amount of water that you can get into a volume of air. Here I've got unsaturated, perhaps that should be non-saturated or whatever. It's possible to fill in values anywhere here because, for example, say at 10 degrees, there is a maximum theoretical and real limit based on the laws of physics that you can get to. So at 10 degrees, the most water you can get into the air is at this point here. And if we go along on this point here, we can see that that's about whatever, 9 grams per meter cubed. So that's an absolute. So that is basically, that's the key line. That line defines the relationships here, and that is the laws of physics. And I'm afraid we cannot change the laws of physics, as somebody once said.
Completely cold. It'll take 30 minutes to regenerate them.
Ship's outer skin is beginning to heat, Captain. Orbit plot shows we have about 8 minutes left.
Scotty, I can't change the laws of physics. I've got to have 30 minutes.
So yeah, it might have taken Scotty 30 minutes, but I'm sure Kaylee could have done it an awful lot quicker, and we're not going to spend 30 minutes talking about this. So this line here is this is key, and this is, by understanding this, this is how we can do this without maths. This line is also known as, and you will have heard of this, the dew point. In fact, people talk about it as a dew point, but obviously it's a line, and what this means is that we can figure out for every single temperature what the max amount of water is within that, and this is absolutely key. Now, the other thing that this line is 100% relative humidity. So that's all 100% relative humidity is the maximum amount of water that you can get into air at a particular temperature. And likewise, we can have 50% relative humidity, 75%, 25%, anywhere in between. And the lines on here, let's just, what colour should we choose? Let's choose red because I've got red in my hand. We can actually draw another line, which is the 50% relative humidity line, all the way along here. Yep. So what that means is that's the line at which we've got half as much water as we could theoretically put in for the absolute maximum on this. So that is, and one of the reasons why 50% is fairly key, by the way, is that there is a temperature which has been deemed to be the most comfortable temperature, which is 22 degrees. 22 degrees at 50 degrees relative humidity, around that sort of area, that's the most comfortable. That's what we're normally sort of aiming for. If the relative humidity goes down below that, you can have problems with, I think that's where viruses and various bugs like to be. If the relative humidity is higher than 50% or much higher, then that's where mold and so on starts to go in. This is very dependent on what part of the world you live in, because we kind of get used to a certain amount of moisture in the air. But let's take that 22 degrees. So for example, actually I'll use a different colour. I won't use red, let's use orange. So at 22 degrees centigrade, let's take this up to the line. Oops, it's not very straight, is it? Take this up to the line, and that is the most comfortable thing. Now what we're looking at here, let's talk about condensation for a little bit, because I'm sure you'll have heard of dew point, and that has to do with condensation. People say, oh, you're okay until you hit the dew point and then you get condensation. And condensation is literally, we know it, on a cold day we breathe out and we get a load of sort of fog coming out of our mouths, or on a cold morning on the boat we wake up and we find that there's condensation on the inside of the windows. In fact, on a boat we normally wake up and find that there's condensation literally everywhere in the boat. The whole of the boat is kind of dripping wet with water. And the dew point is basically when the temperature changes or drops to that point where the water becomes saturated, so it cannot hold any more water in vapour form and it has to turn into liquid. So let's imagine that we're bobbling along quite happily at 22 degrees at 50% relative humidity, and then all of a sudden, for whatever reason, the temperature drops. What does it have? The question is, what temperature does it have to drop to actually cause condensation problems? And we can easily calculate this by taking this line along here, So what we're doing is we're going along the absolute humidity line. So we're keeping exactly the same amount of physical water in the air, going along until we hit the dew point. And then we are coming down to see what that temperature is about there. Hopefully this makes sense. I've drawn that rather badly, but so basically we come to 11 degrees centigrade. So with this amount of water in the air, i.e. the amount of water that we have, which is what? It's kind of just about 9, 10, about that sort of level. So keeping that amount of water in the air and then lowering the temperature. If we lower the temperature to 11, we get humidity. Now, how might we do that? We might do that by all of a sudden the temperature overnight drops. We turn the heater off or whatever, the temperature drops, and then we start to get humidity. Or more likely, in a boat, we're in a cold environment and the cold outside, the thickness of the hull is quite thin with the fiberglass. The hull side is thin. We see this on glass a lot. They're not very good insulators. And the inside, say the outside is 3 degrees or something, the inside is likely to be less than 11 degrees. And if it's less than 11 degrees, you absolutely will get condensation. That's how the dew point works, and that's how you can calculate it from this graph. Let's take another example, because the key thing about this is that hot air, oh, you get to choose a different colour. I'm going to use pink. The hot air can hold a lot more water than cold air. So let's imagine, for whatever reasons, that the relative humidity, I managed to keep the temperature the same with my lovely little diesel heater, but the relative humidity goes up to 75%. Let's just quickly draw a 75% line in, switching back to red. See, this is why felt pens are so useful. You literally could not do this with computer generated graphics, could you? You have to use a felt pen. So that's the 75% line, yeah. And you can see that sort of all these curves, and you can see how the curves would sort of work. So let's imagine we could keep to 22 degrees, but we go up to 75%. So the question is now, what would the temperature have to drop down to on the walls of our boat, on the hull of our boat on the inside, for us to start to have condensation problems? Well, it's exactly the same principle. If I draw a line along until it hits the dew point line, and then drop that line down, and that's about 17 degrees. Does that make sense? So we will start to have condensation problems at a much higher temperature with a higher relative humidity. I hope that's kind of fairly obvious, but it doesn't feel obvious to us, because sometimes we think that cold air holds a lot more water, and physiologically the simple reason for that is we don't have wet and cold sensors in our body. We only have cold sensors. Cold plays a psychological trick on us to make us think that we feel wet, but cold air actually contains much less water. So you can see at these levels, even if let's say the air was at 3 degrees, and imagine it was at 100% humidity. Even at 100% humidity, it would only hold 4 grams per metre square, which is about half of what it would hold at 22 degrees and 75% of relative humidity. So warm air holds an awful lot more water, and my argument is that what I want to do is I want to take the dry air in from the outside, heat it up, and replace the wet air from the inside. Right, so, but is this a big problem? Why won't the air just stay at 50? If the air's at 50% and I can do some insulation or something on the hull, which we'll have a look at in a minute, why would that be a problem? Well, let's have a look at, what colour shall I use? So let's use a light green. How much moisture do I actually have to put into the air in order for us to get this problem? So if I take these lines, again not very straight, from our 50% at 22 degrees and our 75% at 22 degrees, I want to see how much additional moisture I need to put into the air, which I think that's about 5. Let's call that about 5. So if I put in 5 grams per metre squared into Serenity, that would move the condensation level up to 75%. Serenity, I reckon, is about 20 metres cubed in terms of volume. So 20 times 5 is 100. Is that right? 20 times 5 is 100. Yes, of course 20 times 5 is 100. So I would need to put in 100 grams, which is 1/10 of a litre, which is actually not very much. This is surprising. I hope I've got my maths right. I will check this afterwards and put a little comment if I haven't, but even to me that seems like a very small amount. And that comes through from boiling the kettle, making a cup of tea, cooking. The very act of me breathing over a 24-hour period, I will breathe out, and even if I'm not sweating, moisture will come out of me at the rate of about 700 millilitres per 24 hours, which if you do the maths on that, means that, sorry, I've written this down somewhere, so about 1.5 grams per hour is going into Serenity. If I do this experiment over 4 hours, I'm pretty much at that limit anyway, so just sitting there breathing, and I'm probably going to make about 5 or 6 cups of tea in the time I'm sitting doing that. So it's very easy to get this up here. Who knows, I might even get it up to 85%. So hopefully that makes sense. We didn't have to do any maths, we can just use these. These diagrams are easily found on the internet and so on. You can print them out, and I'll be looking at these when I actually do the experiment. But the next question is, well, that's all very well and good, but if it's 3 degrees outside, as I mentioned, obviously what I need to do is to make sure that the inside of the boat is either at more than 11 degrees, if we're at 50% relative humidity, or greater than 17% if we're at 75% humidity. I'm really looking to keep it at this level, so I'm going to work this out based on 22 degrees and 50% relative humidity. That's what I'm aiming for. So how much insulation do I need to put in to that? And I'm talking about insulation here specifically for condensation, because what can I do to reduce the condensation? Well, as I said, I can either put in insulation to make sure that the inside of the hull doesn't get below 11 degrees, or I can actually suck the air out using and in this case it would have to be a desiccant dehumidifier, because at these temperatures a compressor type simply wouldn't work. Again, laws of physics which we won't go into. When I was living abroad for 2 years, I never had one single problem with condensation. I used a desiccant humidifier. Let me show you just a quick clip of that. Right, so this is the MECO DD8L Junior desiccant dehumidifier, which I used as a liverboard. Had it plugged into the mains. It uses quite a lot of power when it's going at full tilt, 600 watts, for sort of normal running. When it's actually going 300 watts, and I think when it's just ticking over 30 watts. So it was ideal. I never had a single problem with condensation. In fact, I used to be able to wash clothes, hang them up inside the boat, turn it up into full power, and it would get rid of all the water. So yeah, that device was great, but it uses a lot of power, as I say, up to about 300 watts. So I could put that in, and then it really wouldn't matter anything else, because I could actually suck the water out and keep this down. So I can either do that, I can stop breathing and hold my breath and not do any cooking. I can do insulation, and I'm going to do an I can suck cold air in from the outside. So what I'm looking to do in the experiments is to see if it's possible to keep the level of humidity down, but next I really want to figure out keep the level of humidity down by taking in cold air from the outside, and whether there's any difference between doing that or simply recycling the air. Because obviously if I just recycle the air and heat it, it's going to be cheaper to heat it because I'm heating hot air, but how much does that raise the relative humidity? So let's have a look at how to calculate what sort of insulation I need to stop condensation. Here we go, this is a different diagram. So this is the outside of the boat, this is the hull of the boat, which is about 8 millimeters of fiberglass, and this is the inside of the boat. So let's assume that outside we've got about 3, this is a scale in degrees, by the way, 0, 10, 20, 30 degrees. And what I'm going to do is to draw the temperature gradient across this. So it's just a way of visualizing this. So inside we've got 22 degrees, outside we've got 3 degrees. What's going on here, and what does the temperature gradient look like, and how does that affect where our dew point might be? Now, I know that I'm very much simplifying these thermodynamics, because actually this isn't a static picture. The heat would be flowing from the inside to the outside, and I'm assuming I can keep the temperature at 22 degrees, where in fact I need to pump quite a lot of heat in to make that happen. So this is a sort of an idealized situation, just to make it simpler. But basically, yeah, let's do this in green. 3 degrees, 3 degrees, 3 degrees, 3 degrees, slightly higher where it hits the wall of there, because this is the heat coming out. So that's there's going to be a bit of warmth escaping there, and then we have a bit of a temperature gradient going through the fiberglass, and then inside, as I say, we're at 22 degrees, and this isn't accurate, this actual temperature here. So this is almost as if we had a little thermometer at every single level here. And the key thing is this temperature here, right on the surface. So if the temperature here is less than the dew point, which we calculated just now, then I will get condensation. Laws of physics, I simply will get condensation, no ifs, no buts, no maybes. If it's greater, I won't get condensation. Yep, and I hope from what we've gone through before that's absolutely clear. So let's talk about putting on some insulation. I love felt pens. I'm going to have some orange insulation, and what I'm probably going to be using is Armorflex. Let's put a little thing of Armorflex. You've seen it. Mads at Sail Life, when he was doing what was the name of his first boat? When he was doing Obelix, used Armorflex, and it's great, and it's specifically designed for industrial uses to do with condensation. It's also got very good R values and lambda, which I'm not going to go into in terms of actually insulating in terms of heat. I'm looking at it here specifically for insulation. So let's stick some Armorflex on the side of here. Let me just remember, I'm deliberately going to make an air bubble there, just to show why it's important to make sure you don't have air bubbles. So that's my Armorflex gone on there. Armorflex is closed cell. It's very good insulation properties, very good at resisting moisture problems and so on. So I've stuck that against the side of the boat. Let's now have a look at what the temperature profile is. So again, it's exactly the same here. This is 3 degrees, 3 degrees, 3 degrees, a little bit higher at this point. A bit of a profile through here, and then this is the bit that's really, really different, is that this is specifically an insulating material. So again, imagine I've got a thermometer at all these points, so I'm measuring the temperature through here. Now the key is what we're trying to do to avoid condensation, and I've not mentioned the relative humidity and so on here, that's kind of irrelevant at the moment, we're just talking about the principles. Let's imagine that was the dew point. Yeah. Now the dew point here is inside the material. That means that everything to that side is at a temperature less than the dew point, and everything to that side is more than the dew point. And what that means, if we can get the dew point inside the Armorflex, we will not get condensation. Does that make sense? We will not get condensation if this dew point, and as I say, imagine we could have thermometers here, is inside, we will not get condensation. And I prefer this way of looking at it to looking at it this way. But, and this is a big but, I said there's an air bubble here. That air bubble is the wrong side of the dew point. I will start to get condensation there. This is called interstitial condensation. It's a massive problem with buildings and houses, and if you haven't got this absolutely stuck on with no gaps, you will, even in small air bubbles, you will start to get interstitial condensation where you will start to get mould, you'll start to get all sorts of problems here. I think this is why people with steel hull boats like to use that spray foam, so it sticks on and you absolutely got no air gaps at all. And this is why I'm very keen actually to try the Armaflex with the self-sticky background. I think you have to prepare the surface really well and then really press it on. As you know, I've mentioned before, I do not like contact adhesives, so I would like to try out the self-sticking Armaflex there. But what I haven't talked about is, based on the relative humidity and all the other temperatures, how thick does this need to be to make sure that the dew point is inside? And that's what I'm going to have a look at next. So hopefully I haven't confused you too much. I've tried to make this as simple as possible, but no simpler, which is something that Einstein said about making explanations of things. So we've already seen that my argument is that in order to keep a comfort level and keep relative humidity down, we should draw cold air in from the outside, and that's what I'm hoping to do in the experiment that we're all going to see in the next video. And you know, we might find that actually, although the theory is true, it doesn't make an awful lot of difference, so it might be more important to figure out how easy it is to get the air from different places. My own personal view, before doing the experiment, I think it will make a difference, and I think it is important to draw the air in from the outside because it is a lot colder. But on the other side, that might be a lot more expensive to do, because I might need to have the diesel heater running almost all the time to do that, and so a balance needs to be made. And part of that balance could be made in looking at what sort of insulation material, and I've mentioned Armaflex, and how thick that Armaflex should be on the outside of the boat. So let's have a look at this diagram here. What I've done is I've taken a few examples and I've used a tool that Armaflex have got online. I'll put a link to it below. So you can feed in various parameters. Now this is for pipes. So what I've pretended is that Serenity is a big plastic tube 3 meters wide and 8 meters long, with air on both sides. There wasn't the thing specifically for fiberglass. I think plastic is close enough. And if we have a look at this, you can see down here on the left hand side, and I've got this in front of me, so I'm sort of staring at this. 3 degrees, that's the outside temperature that I want to work with. That's a reasonable temperature, I think, to start working, and you can change the temperatures and play with this. Then we've got this 8mm bit, that's the actual fiberglass, that's the hull. And as you can see, the temperature is slightly higher at the hull, but you'd expect that because of the heat escaping. And then on the inside of the hull, you can see it's a 6.7, so that's the temperature at that point, which is measured, because this is like in the previous felt pen drawings that I showed. This is just using the temperature gradient. I've done this for 50% relative humidity, and this is the key thing, because obviously, as we looked at previously, the dew point is dependent on the temperature and the relative humidity, those two things, and then we get an absolute humidity from that. We can work out the dew point from that. So all this fancy software is doing is working out the dew point. And then we can see there's 3mm. It's worked out that I need 3mm, which is not very much of Armaflex. And then there's another little layer. That little layer is the sort of the spongy vinyl stuff that you put on the outside. Maybe I'm going to put that on, maybe not, I don't know. And we can see that on the surface of that it's 13.3, and based on the fact, and the inside temperature is 22, so we worked out before, and we know this, that the dew point is about 11 degrees, and what we can see here is that the dew point is inside the thermoflex. Remember what I was talking about in the previous thing? So this means that we will not get condensation inside, because the dew point, the temperature, is effectively inside. And this is a really thin layer of, I was quite surprised at this. I thought this would come out a lot thicker. And remember, this is not for insulation, this is just to stop condensation. It might be that I need a lot more insulation to actually keep the temperature up, but that's not what I'm calculating here. This is just for condensation. So let us have a look at another example, and all I'm going to do here is I'm going to keep the temperature the same, 22 inside, 3 degrees outside, and raise the dew point up to 75%, which we did before. And if you remember, the dew point came out about 17 degrees, I think it was. So here we go. Temperature outside is 3 degrees, 8mm of hull, and we can see that the software has actually recalculated and calculated that we need 13mm of Armaflex. And by the way, you'll see that the temperature here, the gradient through the fiberglass, has actually now changed, whereas before it was 6.7 degrees just inside the boat, it's now 4.7, and that's because of the dynamics of the way that the temperature works, because it's the heat going outwards, remember? Stuff actually I said I wouldn't talk about, so I will stop talking about that now. The dew point here is just inside of 17.4, and the outside wall is at 17.6, so again the dew point is just this side, which means that I will not get condensation. It only needs to be just inside. But what we notice is that we've gone from 3 millimeters with just a small increase. I would say that going up 75% is a small increase of relative humidity, and we're now at 13, so that's an extra 10 millimeters that we need to stop condensation. So the difference, if you get the relative humidity wrong, the difference is massive, and this is why I maintain, it'd be really funny if I were completely wrong by the way, this is why I maintain that it's really important to take the dry air from the outside, because you need to keep that relative humidity down, and the best way I think of doing that is by taking air that's got a lower absolute humidity, i.e. drier air. Take the dry air from the outside and put it to the inside. Okay, right, nearly at an end of this. Let's do one more example, because this could well happen, and I've certainly been in Serenity when these problems have happened. And here we have -10 outside. Inside I've kept it at 22 degrees, and I've assumed, I haven't written it, but I've assumed a relative humidity of 50%. Now this is interesting because obviously we can see the temperatures are very different. At the outside of the hull it's -7.8. That just shows how cold it is and the fact that the heat is migrating to the outside more quickly. The dew point is well inside the armour flex here, the dew point being 11.1, which we know, we've calculated that several times. But this is interesting, is that the thickness required is only 10 millimeters. So it shows that the bigger change in terms of how much insulation you need is not to do with the temperature outside, it's to do with the relative humidity inside. Wow. So that was the simple one. I hope you didn't find that too complicated, and if you know about this stuff, I hope you didn't find it too simplistic. But let me just run a little advert up here, because I want to say, you know, I don't monetize this channel. I don't do Patreon, but I thought, wouldn't it be lovely to get a sponsorship from Staedtler? I do use a lot of felt pens, I do use a lot of cardboard. I'm not expecting to get a free catamaran from Outremer like Vagabond and etc. do, but if anybody from Staedtler is watching, then I've even come up with an advertising slogan, Alle Staedtler oder was? And that's for my German viewers who will understand the relevance of that. So yeah, felt pens, that's all you need to do a boat. I shall see you very shortly, because I'm thinking that the next video will be coming out, if not in a matter of hours, certainly in a matter of days, because I'm all ready to do the experiment. I'm just waiting to get 2 days or 3 days in a row with about the same temperature so I can run this experiment a couple of times, and let's actually see what this stuff does in practice. So thank you for your patience, and I will see you next time.